Empirical formulas is a subtopic in Chapter 6 and a very interesting one. Here you see a picture of an ancient chemist with his distillation apparatus. Chemistry is an empirical science involved in measurement and relationship between quantities. So this is why this topic kind of brings you back into how formulas were determined in the very first place. It was Joseph Louis Proust. He was a French chemist who showed that relative quantities of any pure substance remains unchangeable. This is a crucial empirical evidence that supports the law of definite proportions, which holds that elements in any compound are present in fixed proportion to each other. For instance, let's take water. This is an interesting picture of the decomposition of water. Here's oxygen gas formed and the hydrogen gas. You can notice the volume is twice as much hydrogen to oxygen. If this is weighed, we'll find out the sample produces only 3 grams of hydrogen, right there's the 3 grams, and 24 grams of oxygen. How could we, from this empirical evidence, could we determine the empirical formula of water? Well, the first thing we would do would note the mass ratio. There are 3 grams of hydrogen for 24 grams of oxygen. And then ask yourself how many moles of each element is formed. And remember that if you use the conversion factor that 1 mole of hydrogen is 1.01 grams, that's molar mass found on the periodic chart, you could do this conversion. 3 grams of hydrogen converted to 3 moles of hydrogen. And oxygen, 24 grams of oxygen converted to 1.5 moles. Therefore, the mole ratio for water is 3 moles of hydrogen for every 1.5 mole of oxygen. Now, normally formulas are given in whole number ratios, but we can write this pseudo formula for water, H3O 1.5. Now we have to work to get this to whole number ratios. Well, one of the first things you can do is divide each subscript by the smaller one. So if you divide 3 by 1.5, you get 2, and 1.5 by 1.5. So the formula becomes H2O, and we're done. So our empirical formula for water also happens to be the correct molecular formula. If, after dividing the smallest number of moles, the subscripts are still not whole numbers, then we sometimes have to resort to a multiplication of the decimal fractions. If you recognize that if you have the decimal fraction about 0.1, multiply it by 10. 0.2 you multiply by 5 and you'll get 1. 0.25 you multiply by 4 and you'll get 1. You multiply by 3 for these recognizable decimal fractions give you which whole number to again multiply after you have the mole ratio. So in a protocol for getting the empirical formula is write down and get the given masses of each element present in the compound, and then convert each of the masses to moles using the molar mass from the periodic table as a conversion factor, and then write down a pseudo formula with the subscripts of the moles given from step 2. Then divide all the subscripts by the smallest subscript. And if the subscripts don't turn out to be whole numbers, again multiply them by a small whole number according to the previous table. For instance, suppose we want to calculate the empirical formula from reaction data. We found that 3.24 grams of titanium reacts with oxygen to form 5.40 grams of metal. So this given quantities, you have to use the law of conservation of mass to determine the mass of oxygen. So you got the mass of titanium and the mass of titanium oxide. So if you subtract the mass of titanium, you'll get the mass of just oxygen. So now you have the initial mass of each element, of titanium and of oxygen. To find the mass, so this shows you that calculation. Now you can convert the mass of each element into moles. Another way of finding molecular formulas from empirical formulas is needed. The empirical formula is going to give you the smallest mole ratios, but the molecule might actually be built up of multiples of that. So generally the molecular formula is the empirical formula multiplied by some whole number. We can easily find this because the molar mass is equal to the empirical formula mass times n, or n is equal to molar mass divided by the empirical formula mass. Let's see how this works. Suppose we want to find the molecular formula for fructose, the sugar found in fruit. And its empirical formula is CH2O, 1 carbon, 2 hydrogen, oxygen. But its molar mass is 180.2 grams per mole. So what you can see is that it consists of more than 1 carbon, 2 hydrogen, and oxygen, but some multiple of that. The molecular formula is a whole number multiple of CH2O. So let's calculate that. The empirical formula of CH2O is simply 1 carbon, 12.01 grams, plus 2 hydrogens, plus 16 is 30.03 grams per empirical formula mass. If we take the molecular formula mass and divide by the 30.03, we end up with 6. So we now know what N is. We know that the molecular formula for fructose is CH2O times 6. So it's C6H12O6. That's the molecular formula for fructose. In general, calculate molecular formulas for compounds by using the molar mass of the empirical formula and then divide the known molar mass, or multiply the empirical formula by n to get the molecular formula. Multiply the subscripts in the empirical formula by n to arrive at the molecular formula. So chemistry is an empirical science. Mass ratios, corresponding mole ratios, and percentages. The mass to mole conversion using the periodic table is very important.